It's Joe Wheaton from Utah State University, and I'm going to talk to you specifically about how to read riverscapes for structural forcing. In the photo shown here, this is a beaver dam complex up on Spawn Creek. It's actually where I take you on a virtual field trip. And what we can see is that what would otherwise be a single thread little mountain stream is structurally forced by this beaver dam activity. They're bringing wood, they're building dams, they're backing up water, they're spreading water out, etc. So this is what we're going to learn how to read a little better. So we want to build your intuition about the key processes of wood accumulation and beaver dam activity, but broken into those component pieces we spoke about in Module 1. So hydrologic, hydraulic, geomorphic, ecologic. So it's kind of a crash course in fluvial geomorphology. And again, the Frias and Brierly is a good introductory text. Recall from Module 1 also the principles. Principle 2 that structure forces complexity and builds resilience. And in this example, it's a beaver dam that's shown as that example. So the best way, in my opinion, to do this is to get out in the field. There's just no substitute for it. But given that this is a virtual workshop, what you can do is you can go to this link and you can watch the virtual field tour. I'm just going to take you there briefly. In here, there's a map, so you can kind of zoom in and around, and indeed, if you zoom in, you're going to start to see beaver dams. Okay, so that's sort of helpful. The red line is basically a guided virtual tour, and the yellow line is a self-guided tour coming back down. The guided virtual tour, there's a little introduction for what it is and what it's about, and then there's basically some jerky GoPro footage. Mountain stream. It's the single thread channel here on Spawn Creek, and I can see a little. So it's really just me explaining to you, if we were out in the field, this is what we would do. This is what we would look for. This is how we'd read this riverscape. And then the self-guided tour is basically, it's actually the same riverscape, but coming down a slightly different part of it, and with nothing more than just the eyes. So I don't talk at all, and you can just tally off and make observations. There's actually a little survey that you can take if you want. There's also this drone footage, which just shows you this riverscape that we take you on this virtual tour in. Okay, so that's kind of fun, and it's not as fun as being in the field. And there's some other albums and resources, some explanations from Temple Fork. There's things to go check out if you want to go deeper, but to just do the basic part, you're talking about an hour and 10-minute video for the guided tour and a 20 some odd minute video for the self-guided tour. Okay, so you can do that on your own time. And just to place us back where we're at here, we're just kind of picking off these questions one at a time that relate to this more generic planning portion of the conservation planning process. That was interesting. So anyhow, one of the key questions, this decision point really is, it's a screening question. Is the riverscape structurally starved? Because if it isn't, low tech may not be appropriate. There may be other things that you might want to consider. So we want to unpack that. Okay. We want to see, am I in a situation like this where it is a bowling alley and there's, other than a few cow pies, there's nothing in it, or in a bowling alley and other than a few short-lived alder branches and relic boulders, there's just not much in the way of structural elements. Okay. So we've talked a bunch about this in the principles lecture. We've revisited this in Nick Bowis's lecture in Module 1. And so this sort of pathway to complexity via structural forcing, that's what we're trying to unpack. And we're going to start with a little elaboration of hydraulics, okay? So hydraulics is basically a function of climate, hydrology, geology, geomorphology, but it's not those things. Those things are very important deciding factors. So it doesn't equal those things. What does it equal? Well, there's some hints on the screen. We'll start with thinking about what a hydraulic versus a hydrologic model is. A hydraulic model takes as a boundary condition topography, right? So you give it a riverscape basically, and you feed it discharge at the top. You feed it a flow rate, and then it routes that flow rate through, and in so doing solves for the hydraulics, which are the primary hydraulic variables of velocity and depth. And so right here, we can see in color water depth, right? The darker blues are deeper, same over here. And we can see in this rainbow of colors here, that's the magnitude of velocity, and those are flow vectors. And then this little animation is just showing these things. And so right now you've got this flow coming in on this inside bend. There's a flow separation. That separation is strong enough to produce a shear zone, a flow separation point, that then we have this little eddy, okay? And so when you read a river, the hydraulics matter. They matter whether or not you're a fly fisherman, whether or not you're a whitewater kayaker, a fluvial geomorphologist, or an LTPBR designer, okay? You know, this is not out of any sort of design manual or out of any sort of hydraulics, right? This is like basically a guidebook for boaters, right? So it's telling them, okay, well, you know, flow's coming in this way, you know, look for the seam, right? This seam where two current speeds meet. Look for this slow water behind the walk. Look for this faster water. Look for this slow water in an eddy, okay? So let's unpack some of this. This skill of reading water, if you're a fly fisherman, you probably, or fly fisher woman, you probably know exactly where to cast. Right on the edge of those seams where the fish may be hanging out in the, just like this kayaker is, in this low energy sort of eddy behind this boulder, and not over in the swift water, right? So they can conserve energy, and then if they need to peel out and get back into the current, they can do that right away. Fish do the same thing, conserving energy right along that zone, especially visual drift feeders like trout. Okay, so some definitions for you. This diagram on the left, just so we know what we're looking at, this is a plan form map. This is a hydraulic model output. It has two pieces to it. It has in dark and blue, the shade of blue corresponds to water depth. And then the rainbow of colors and the arrows and the size of the arrows represent the magnitude of velocity, and then the arrows are pointing in the direction of flow. You have a boulder up here, which is this boulder right there, okay? And there's a boulder that's completely protruding out of the water, and there's one that's slightly submerged and flows going over the top, and that's what's shown here. These two boulders are down here, okay? And so you've got this flow coming along, and those two boulders are both out of the water, and you get this flow separation point, okay? And so we call these boulders, they're examples of structural elements. A structural element is any discrete object that directly influences hydraulics. And so in this case, you have this flow separation. The strength of that flow separation creates this seam. And within it, it's such a strong flow separation that on the other side of this seam, we actually have flow reversal. So we have an eddy. So this sort of whirlpool-like pattern. This is because at that flow separation point, The magnitude of the velocity going past it is so strong that shearing motion, it creates this really strong shear zone and eddy. Now notice this one, the arrows are all pointing in the same direction. So this one coming right over this rock. There's a little submerged hydraulic jump right over the top of it. And then this is what we'd call a wake. So an eddy versus a wake is really just two different shear zones, but describing the difference between one that just slows water downstream of it, that flow separation isn't strong enough, versus one that it actually flows in the opposite direction. So structural elements can produce the stars, these flow separation points. We also have some along the margins here. So they can be produced by other features as well. Downstream of those flow separations, you get seams. Inside the seam, you get a shear zone. And then you have some sort of, usually it's not as well defined as the separation, but some sort of reattachment point or zone. And by mapping and identifying these things, you're helping predict zones where you might have erosion, deposition, margins, and force geomorphic units. So it's a really powerful skill to be able to just read water like this. It helps you recognize what structural forcing is doing. Now, a big caveat. You can get really good at snapshots of reading riverscapes. You can get really good. But bear in mind, most of the time when you're looking at a riverscape, it's at low flow. So the art is in inferring whether those patterns exist at higher flows, which may be capable of moving sediment, moving wood, etc. Right? Now, it's wonderful if you can get out at high flows and see that. You can't always. And so that's where some of the art of interpreting these things or investigating them post-flood and starting to learn how these things act at higher flows. So specific examples of structural forcing: shunting, constricting, splitting, slowing down, backing up. We've mentioned those things, okay? I'm going to show you 3 slides that are horrendous. They're out of this paper that I've mentioned before, Fluvial Taxonomy, and they basically are, there's just a simple way that looks at differentiating structural elements. You don't have to use this, but it might just be helpful for helping you appreciate how many things are out there. The first split is whether we're dealing with anthropogenic or natural. And so, you know, the things that you build in a riverscape, the structural elements that you put in, those are anthropogenic. Okay, they may get co-opted and used by the system, but they are anthropogenic. The things that you may find naturally occurring, those would be either of sort of an organic origin, so aquatic veg, beaver dams, debris, large woody debris, riparian vegetation, roots, undercuts, or inorganic like bedrock and boulders. Once you've kind of identified those types, then it's helpful, you can come up with whatever the specific thing is by using these key attributes to differentiate it. So we have the orientation. Is it a diagonal feature? Is it transverse across the channel? Is it streamwise oriented with it? We have the position. Is it margin attached? Is it, or bank attached? Is it channel spanning, mid-channel, side channel, floodplain? We also have the obstruction type. Is it a sieve? Is it a complete barrier, a porous barrier, a deformable barrier? What stages it has hydraulic purchase at, so even at bank flow or just in floods. And then if it is a structural element, it's going to produce a shear zone. It's going to do one of these things, right? Shunt, constrict, split, slow down, back up. And downstream of it, it ought to have a shear zone, and so that would be a wake or an eddy, or if it goes right over the top, could be a hydraulic jump, okay? So this table elaborates what those things mean, okay, in terms of those differentiating things. And then this table, which you can't read, just breaks out some specific examples of the many, many different flavors of structural elements. Again, we're just focusing on beaver dams and wood accumulation, but recognize that that there are tons of examples of these, both naturally and anthropogenically occurring. So, back to something we've talked about. Wood accumulation. Wood accumulation simulated, mimicked with PALs, right? And so we have a margin attached PAL, we have a mid-channel PAL, and we have a debris jam. These are cartoons out of the Asotin, which you heard Steve talk about in Module 2. And these are cartoons that Reed Camp drew. And so you have hypothesized velocity vector responses. So those are hydraulic responses, right, shown with these arrows, where the structure is expected, in the case of this one, to create a constriction jet. That jet, kind of like your thumb on a garden hose, will be maintained, depending on the flow rate, for some distance, and then it loses its energy. And so as it does that, it starts to spread out. This would be where your flow separation point is. This would be your seam. At high flows, you might have a pour over the top of the structure. You might also get a little eddy up here. And so those are your hydraulic responses. Your hypothesized geomorphic responses are sort of shown with the colors. You might get a little bit of bank erosion here, right? This boulder is helping maintain that constriction jet. If it wasn't there, you might get more bank erosion. The fact that you have a jet and then it expands, you might get a riffle downstream of it building up. You might get some overbank deposition. You might get some scour of a pool, etc. Right? And so we've got different responses expected with these different structure types. This is the information at a structure scale, so when we get into Module 4, that you're using to read the Riverscape 4 opportunities and think about how that structural element will engage at different flows. So some of those hydraulic responses are immediate, i.e. at low flow. Some are, you could make these predictions for a typical flood, right? And so we've got a bunch of sort of cartoon versions of this, schematics, if you will, that represent hypothesized responses so that you don't need to draw one of these things every single time, okay? If you come up with a different sort of structure design, yeah, you can make the cartoon once, but think of it as like a standard detail. Like if you're going to build a brick wall, you don't need to draw a plan for every single brick and exactly how that brick is installed. What you need to do is have a standard detail of what a brick looks like, and then you can move on with life. Okay, so yeah, I think that's good enough for now. So back to this question, this screening question: is your riverscape structurally starved? Well, we can go to some arbitrary riverscape here. It's one that we're going to use this afternoon as our example. And we could ask, is it structurally starved? Well, it's helpful to break this out by process. So is it starved of wood accumulations? Well, this is a classic O to E problem. Observed to expected. The easy part is counting whether or not there's any wood accumulations. The hard part is contextualizing that, whether or not you would expect there to be in that environment. But if you just ask if it's structurally starved, it needs to be contextualized with the expectation of what you might have expected there. I reviewed in Module 2, well, review is an overstatement. I highlighted some of the woody debris literature that can give you some hints at this in terms of the expected part of the problem. But it doesn't take a PhD in fluvial geomorphology to look at a system with absolutely no wood and recognize that some wood would have been present and recognize a departure. Okay. Same thing for starved from beaver dam activity, right? You can count beaver dams, but what's its capacity? And we do have models like BRAT, Beaver Dam Restoration Assessment Tool, which allow predictions of existing capacity. And capacity is an upper limit. In certain points in time, it may reach that capacity. It shouldn't exceed it. It may get to some proportion of it, but they help provide some bounds on that. Okay, so you want to look for evidence of what woody veg would be there to support these processes that could be recruited from either floodplains or hill slopes, and look at current conditions that might limit that, right? And so I want to close this section out with a short little exercise, and that exercise is as follows. What you need to do is open up your favorite mapping software. To keep it easy, I'm just going to have you use mymaps.google.com, right? And you can go in and you can create a new map. And what you can do is search for that creek we were just looking at. It's called Coburn Creek, C-O-B-U-R-N. It's in Wyoming, okay? There's actually Coburn Creek Road, which is exactly where I want to take you, right? So, and then you're going to change this to aerial photography. And then you're going to create a layer, and you're just going to start mapping. So I'm going to illustrate this for you. I'd like you to find at least 5 beaver dams, and you can do this in any riverscape. So we come over here, I go to mymaps.google.com. You can see I actually have one there, but I'll just show you anyway. I'm going to create a new map. Beaver Dam demo map. And first thing I'm going to do is change it to satellite imagery. Then I'm going to search for that creek, Coburn, C-O-B-U-R-N, Creek, Wyoming, Coburn Creek Road. Okay, took me right there. Put a little push pin on it, even added that to my map. It's already got an untitled layer, so I can just call this, Beaver Dam map. Or Beaver Dams, I should say. It's a layer. And, oh, look at that. There's actually a few just right here, yeah? So I can then go, it says add places by importing data or by drawing. Well, here's drawing tools. So if you wanted to draw a beaver dam crest, that's one right there. So beaver dam crest, right? Save. And look at that, it gave me a measurement. It's 58 feet, okay? If I wanted to map out a pond, it looks like I've got a crest down here. Something like that, maybe. Crest 2, and you can have notes. You can even put a little photo associated with that. 177 feet. You can also, I thought there was, oh yeah, they don't have polygons right here. Look at that, it's a little overflow channel. This one looks like it's groundwater fed. Might be some in here. It looks like this is obviously a picture at high flow. You could also just map them as points, right? So there's Beaver Dam. There might be a breached one there. Looks like there's one that's backing water up. And this isn't, admittedly, this place where I'm taking you isn't the easiest place to see them, but they're here. You can see them, right? And so once you get that, then you can use some of these distance tools, and you can start doing things like, counting, like how many beaver dams per kilometer, per mile am I dealing with? Are they dams on the main anabranch? Here's that main anabranch shown at high flow. Or are they dams off on the floodplain that are groundwater, or sometimes along the toe of the slopes that are spring seeps? Okay, so I'd like you to go in this riverscape and just map at least 5, right? You can go to any riverscape, you can play these games. Doesn't mean that your riverscape will have wood or have beaver dams, but this is the exercise. So back to the last slide here. that's all we got. And in the virtual workshop, we'll have a little Q&A on this. Okay, so just an introduction to structural forcing and thinking about that. Reminder that the real substance of this is getting out in the field and doing it. There's a lot you can do from a desktop too. So have fun with it.